In spite of appearances, this programme is not about fruit. Coffee, please. Did you know that over 150 years ago, one of the greatest scientific institutions in the modern world was set up with money from the illegitimate son of the Duke of Northumberland? A guy whose scientific qualifications included discovering a better way to make a cup of coffee. Strange, but true. But that's the way it was back then. Anybody could be a scientist, like this guy was. Name of Smithson, who gave America $2 billion in today's money because he reckoned the country needed to spread the light of knowledge. Ironic, since this programme will end with knowledge of light. Oh, there's the place I was talking about, named after James Smithson, the Smithsonian. A few statistics. 140 million things in the museum collections, over 25 million visitors a year, all getting lit by knowledge. Smithson would have been proud. And research projects all over the world, including this archaeological dig in the Middle East, picking up treasures and a suntan. Speaking of which, apart from the coffee, Smithson also did a lot for sunburn, and poison ivy, and cosmetics, and diaper rash, and zits, and photocopiers, and tyres, and ceramics, which is where a lot of the gunk in this bottle gets used. Smithson discovered it when he was crystal hunting in England, and came across stuff like this. It's called calamine, as in calamine lotion, which is made of one form of the crystal. OK, no big deal, unless you suffer from sunburn, or poison ivy, or diaper rash. But there's something very strange about calamine. So, for a few moments, here comes a brief dissertation on everything you ever wanted to know about crystals. Don't worry, it's electrifying stuff. In 1880, a couple of French physicist brothers discover the amazing secret of crystals like this. If you slice a bit out, and then squeeze it, put pressure on it, the crystal changes shape slightly. And when it does that, it gives off an electric charge. And the more pressure you put on it, the more electric charge it makes. And it does the opposite. Zap it with an electric charge, and it changes shape. And the bigger the electric charge, the more it changes shape. OK, now for what you can do with all this. Put two crystal slices up against each other, and hit one with electricity. It changes shape, squeezes the other one, and it makes electricity. The same charge that affected the first one. So if the first crystal is affected by an electric field, the second crystal will react. The whole thing's a tiny electricity gauge. Now, don't nod off, because, as you will see, this turns out to be a tale of genius and dark passion and behaviour that perhaps can best be described as bohemian, in more ways than one. Because one of those two French brothers working on crystals, a fellow called Pierre, marries a girl called Marie who comes from Poland, and the reason they both care deeply about where I am now, down the bottom of a mine in the Czech Republic, together with this very slightly radioactive water, is because this is where they get the raw material on which they will use their little electricity gauge and change the entire world. Here's where the raw material comes from, the northern mountains of the Czech Republic in Bohemia. And it comes out of these mountains by the ton. Here's a bit. It's called pitchblende. And before our curious couple get interested in it, it's used for colouring ceramics. And it's mined here, just outside the little town of Yakimov, down there. Oh, by the way, that use of pitchblende to colour ceramics was something to do with glazing pottery and nothing to do with my story, so I won't go on about it. OK, in 1896, a German called Röntgen totally blows away the world of science with one of the most amazing discoveries anybody has ever seen. Well, I suppose I mean seen through. This. X-rays. So everybody immediately jumps on the bandwagon, looking for more mystery rays and what you might do with them. It only takes a few weeks, and bingo, some Frenchman repeats the trick. Only what he comes up with is even more stupefying. Because what he does is fiddle around with some of that stuff from around here I showed you before. Pitchblende. One of the things you get from pitchblende is uranium. And it turns out, if you put an object between the uranium and a photographic plate, and then leave the whole shebang in darkness, the next time you look, there's a shadow of the object on the plate, as if the uranium had been giving out some mysterious, invisible light. The other thing uranium does, our Frenchman discovers, is to very slightly charge up the air around it. But this is ho-hum stuff, and nothing at all to do with the exciting mystery rays. So our Frenchman kind of ignores that bit. But not that Franco-Polish couple I mentioned, Marie and Pierre, family name Curie, who, you will recall, are using that little crystal electricity gauge, right? In 1898, the Curies are getting concentrates of various materials by boiling and distilling them, and one of the things they do that to is pitchblende. And their crystal electricity gauge identifies an amazingly powerful electrical charge in the air all round the stuff. One night, they pop into the lab and there's the sample glowing in the dark. The world gets radioactivity, and they get the Nobel Prize. Soon, everybody's decided slightly radioactive water is good for your health. Speaking of health, unfortunately, Marie's husband Pierre is killed by a truck not long afterwards. 5 years later, the widow Curie is sending out loneliness signals to the guy who has been their lab assistant for years, a fellow called Paul Langevin, who gets the message, and in no time at all the two of them become a bit of an item. And a national scandal. Because back then, widows are not supposed to send that kind of signal to unattached men. Of course, given what Langevin is about to do with the Curie's little crystal gizmo, receiving signals is right up his street. You're watching Langevin's use of the crystal right now, because that's how this submarine hunter knows when to fire her depth charges to best effect. Because thanks to Langevin and what's called the Langevin sandwich, the ship knows she's sailing over the top of an enemy sub. Here's how. Attached to the hull of the ship is a small kind of dome structure, and inside, that Langevin sandwich I mentioned. A slice of crystal sandwiched between two plates of steel. OK, you recall the crystal reacts to electricity by changing its shape each time you zap it. When that happens, the vibration caused by the changing crystal shape makes the steel plates vibrate too. And when that happens, the vibrations are really powerful and send out waves into the water surrounding the dome, like this. The waves go out in all directions, and when they hit something like a sub, they bounce back, put pressure on the crystal, and it makes electricity. And that's what generates the pinging noise that tells the sub hunter where the sub is and what to do about it. The Langevin sandwich becomes known as sonar, and early in World War II it makes life very uncomfortable for the German U-boat wolf packs lurking under the surface, and helps the Allies win the Battle of the Atlantic. By the end of the war, thanks to sonar, the Allies have sunk 782 U-boats, or forced them to surface to surrender. Mind you, in spite of that, the wolf packs take their grim toll. Over 23,300 merchant ships get sunk between 1939 and 1945. Here's one the U-boats didn't get, the USS Jeremiah O'Brien, the only one of her kind still in one piece, anchored in San Francisco as a tourist attraction. She's a special kind of ship, designed to carry supplies and American troops to Europe through thick, thin, and wolf packs. Not very impressive looking, is she? But you should hear what they say about her at the time. When the project to build these ships is announced, They are referred to by President Roosevelt as, quote, dreadful-looking objects, unquote. And to add insult to injury, when they are launched, they have no radio detection finders, no fire detection equipment, no emergency power generators, and no lifeboat radios. But with a war on, the name of the game is fast, and above all, cheap. They're cheap because they're standardized. Every single one of them is exactly the same. You go from one ship to another, and you don't know you've left. And that's because nobody's ever built a ship this way before. The shipyards that built the Jeremiah look more like car plants, where they literally assemble a ship from 30,000 parts made in 30 different states. Okay, let me do a quick catch-up. We're here assembling wartime ships because the Curie's crystal electric gauge got used by Langevin to develop sonar that helped to knock out German U-boats attacking the ships you're looking at being put together faster than the U-boats can sink them. The first ship takes 257 days to get built. By 1942, they've got it down to an incredible 15.5 hours. They carry 9,000 tons, go at 11 knots, and nobody thinks they'll last longer than 5 years, even if a U-boat doesn't get them first. All in all, they build 2,710 of these ugly tubs, and between them they save Britain and tens of thousands of lives. Thank you. And if I tell you that the first one to be launched is named the Patrick Henry, you'll know what these ships are called. Liberty ships. If you take a careful look at this Queen of the Sea, you'll see why back in the 1940s putting a ship together that way is such a calculated risk, and why they managed to put them together so fast. Because at the time, they're doing something nobody's ever tried before. The Liberty is an all-welded ship. That's another reason why during World War II, this ship is such hot stuff. The point about welding a ship is it's faster than joining the bits together with rivets, but not as strong. Okay, oxyacetylene welding. The oxy stands for oxygen, and the acetylene I'll get to in a minute. But the thing about mixing oxygen and acetylene is the flame. It burns at about 4,000 degrees centigrade, 1,000 degrees hotter than any other gas will give you. So it's great for welding the sheet steel Liberty ships are made of. So the Jeremiah O'Brien is a one-piece ship. Going aboard is quite a theatrical experience. And speaking of theatre, and the acetylene I said I'd get back to, it's acetylene that leads to this funny-looking object, which is something that changes life in the theatre, and something that puts the phrase bright lights into your vocabulary, because this funny-looking object is the arc light. Okay, now for a quick burst of mysterious 19th century chemistry. You get acetylene gas by slowly dripping water onto calcium carbide, which some guy discovers you can make by banging high voltage electric current into a mixture of lime and coke. You deliver the current through a pair of carbon rods and do the whole thing in something called an electric arc furnace. This works on the same principle. Look. You run electricity through each of these two carbon rods, and then you slightly separate them. And when you do, you put on your sunglasses. This is the brightest light in history so far, caused by electricity arcing across between these two carbon rods and causing them to burn incandescent. Keeping the rods the right distance apart as they burn away is something a Frenchman called Foucault thinks up. He calls it a regulator, and basically it uses the tiny variation in current as the rods burn away to run a clockwork mechanism that moves the rods, keeping them close together. In the theatre, the arc light is the answer to every actor's prayer. Meanwhile, Foucault has other, more heavenly ideas. The other thing Foucault does can only be described as cosmic. The first proper experimental version of it happens here, in the Pantheon, in the centre of Paris. And it's one of those science discoveries that gives you goosebumps. Foucault takes a heavy ball and attaches it to a great long wire and makes sure the wire isn't twisted. Then he pulls it off to one side and fixes it to the wall with a piece of string. And then, to make sure nothing will influence the swing of the ball in the slightest way, he burns the string. The string burns through, snaps, and the ball starts to swing. Now, here's the bit that boggles the mind. If we move our camera so that it stays in line with this ball, and we do a bit of time-lapse photography, and I sit as still as I can, you'll see what Foucault saw. The ball goes on swinging in the same place, in inertial space, independent of the Earth. What you're seeing now is extraordinary. It's what you'd see if you were watching the Earth from somewhere in outer space. In 1851, when Foucault does this, he finally proves that Copernicus was right. The Earth does rotate. Watch it again. You see what I mean about goosebumps? This is the Earth turning. I said this was a cosmic idea because if you put Foucault's clockwork arc-light regulator together with his inertial pendulum, there's only one thing you can use them for: to save astronomers from eye strain. Put yourself in the astronomer's place, staring up at the nightly show whizzing by. Because thanks to the fact that the Earth spins at 1,000 miles an hour, you're moving around at a fair lick, and the stars aren't. Look at a star field through a fixed telescope, and what you see is, there it was, gone. Foucault's doing that inertial pendulum thing of his, and realizes that the trick to stargazing is to use a clockwork regulator, remember the arc light, to turn a telescope the opposite way to the Earth. So heavenly bodies stay in the frame just long enough for Foucault to do what he does next. Take a photograph. In 1845 he gets the first clear shot of the sun, and then 6 years later, this, the solar corona, and these things here called prominences, which people have always thought were optical illusions. Foucault's photo shows they're real. And then, the first clear detail of these, sunspots, which turn out not to be mountains. Where are we? I mean, in the story. Electric crystals help Pierre and Marie Curie discover what they call radium, and then Langevin uses the crystal to develop sonar that helps save Liberty ships, put together with welding techniques using acetylene made with carbon arcs, also working in arc lights, with clockwork regulators built by Foucault, whose pendulum helps him to take pictures of solar eclipses. And astronomy really takes off. Look. With tracking telescopes, you can take precise enough photographs to spot the smallest changes between one photograph and another. You overlay the pictures, and it's easy to see what you just missed. Watch this spot again. See? And then you can overexpose the photograph, and even very faint stars become visible. And you can really start to enjoy that wonderful nightly show up there. And speaking of shows, that's where Foucault gets his photography from in the first place. OK, this is the 1822 version of virtual reality, called a diorama, and the latest excitement for the Paris glitterati. Now, bottom left is the view the audience gets. Into a spring scene behind a cloister setting, we lower a giant gauze panel, and light it to put a fog effect onto everything. Put a light on the scene itself, and off the fog effect goes, and the scene clears. Take light off the spring scene and onto the snow scene behind, and that's what you see. A painted gauze scene either shows up because it's lit or doesn't because it's not. Boring, right? Wrong. Back then, for the locals, this is boffo crazy Hollywood extravaganza stuff. And all thanks to this French fanatic for virtual reality called Daguerre. Name ring a bell? By 1840, Daguerre's next version of virtual reality, which Foucault will use in his astronomy, is something that gives people cramp. Well, they have to keep still for so long if they want to enjoy the latest rave experience, which is to have their daguerreotype taken. Daguerre's amazing new invention becomes an instant worldwide craze. You take a silvered copper plate out of its case, in darkness of course, expose it to the scene, and then utter those immortal photographic words, "Stay very still, please," and start counting. 1, 2, 3. Developing the picture goes like this. Put the exposed plate in iodine vapour to get a film of silver iodide on the plate. Now put it in mercury vapour that only sticks to the bits hit by bright light. Dipping the plate in hyposulfite washes off the bits not mercurized. Wash everything with distilled water and you get the world's first photograph. And it costs so much it comes in a frame. Now, all the magic ingredients Daguerre uses are known to any chemist at the time. Mercury, distilled water, silver, copper. But there's one new chemical in the mix. Iodine, discovered thanks to a recent accident. Now, you know iodine has all kinds of healthful properties. This is ironic, given the job of the guy who discovers it. He kills people. In 1804, Napoleon's problem, and that of the guy who discovers iodine, is this. The way to win wars is with gunpowder. Key ingredient, saltpeter. Problem is, it's an import, and you can't import when there's a war on. So the French have to make saltpeter themselves. That's okay, saltpeter's made from wood ash, lime, and something Frenchmen make in abundance themselves. Dung. Standing guard over the nation's prime resource, French troops collect enough, raw material to ensure that their chance of victory has not gone down the toilet. And then the guy who's making the gunpowder hits a snag. His name is Courtois, he's a chemist, and his problem is this. The wood ash he also needs, remember? But all the timber they've got is going for shipbuilding. Fortunately, there's an alternate replacement for wood ash, so Courtois gets on with making his gunpowder. And one day, his vats need cleaning out, so he chucks in some sulfuric acid, and out come violet fumes that condense to become what he then discovers is iodine, for Daguerre to use in his photographs. The reason for the fumes is what Courtois has been using as a replacement for wood ash. Where from? Well, find any beach. This one, for instance, in northern Scotland, where a lot of that wood ash replacement comes from. Thanks to the fact that the 18th century Scottish nobility are pretty fed up with living in crumbling ancestral homes with no heat or running water or lavatories. Nope, they'd rather be enjoying the high life down in London. But with no money, no way. And then the wood ash crisis strikes, also in Britain. Well, look around, where do you see trees? And then, yippee, it turns out that the Scottish coastline is positively choked with something else you can use to make wood ash. Seaweed. All you have to do to make yourself a fortune is persuade all those penniless, starving and unemployed peasants who live on your land to collect it for you. This is the easy bit. Since the law at the time prevents them from emigrating to a better life in America, they're desperate for any work, and most of them owe you rent. So in no time at all, they're down on the waterline cutting kelp off the rocks. Kelp is the type of seaweed in question. And turning it into money, that is, wood ash, is a piece of cake. You just, well, burn it in pits, and then pile stones on top to compress the ashes down, which is why making money with kelp is a piece of cake. Because what comes out is cakes of wood ash. Ship these off to the factories in England, where they grind the cakes into a fine powder which they call potash, and Scottish aristocrats call money for jam. The profits from this local slavery are so humongous that soon some Scottish castle owners have enough cash to spare to build more castles, with no heat, running water or lavatories, in which they don't have to live, because now they're having fun spending the rest of the profits down in London. Hey, what can I tell you? Most of these guys went around in skirts. So, thanks to the kelpers, the ash crisis is over. So gunpowder makers can get on with manufacturing their saltpeter. And something a little more meaningful can happen. I refer, of course, to that minor event otherwise known as the Industrial Revolution, for which potash is essential, especially in the underwear business. See, down south in England, 3 decades of hot Indian summers has meant great harvests and cheap food, so spare cash to buy a knockout new foreign fabric called cotton. Once you get the natural grease out with a solution of potash, you've got a really comfortable, cheap, lightweight cloth, if certain production problems can be solved. So solved they are, by machines, hence the Industrial Revolution. And this is also one of those chains of events where technology solves one problem and creates another, which gets solved and creates another, which gets solved and creates another, and so on. Problem number 1, make more of this new wonder cloth, but for the same amount of money. So in 1753, they automate the weaver's shuttle by putting it on little wheels and tying a bit of string to it so the weaver can tug it backwards and forwards. This simple little gizmo doubles output at a stroke, so that's problem number 1 solved. Problem 2, the thread makers can't make thread fast enough to keep up with this new weaving speed. So in 1776, they automate the way the cotton wool is drawn off bobbins and pulled out into thread. So the old thread making by hand problem is solved, and the old thread makers are out of work. But hey, that's progress, right? Problem 3, they've got to make more stuff. So in 1771, a new thread-making machine pulls the thread out and twists it into yarn. Problem 4, the market's differentiating. Some people want even finer cloth for that fancy new idea I mentioned earlier, underwear. So in 1779, somebody sorts that one out with a really nifty trick. Run the thick thread between rollers going at different speeds so that when it comes out the other side, it's much finer. And finer thread, of course, means finer fabric. Problem 5, the real problem, demand goes through the roof. And all this thanks to those Indian summers. The other place they have Indian summers is India, where the cotton comes from. Places like Madras, founded by the English. OK, a quick catch-up again. Electric crystals, sonar, welding, arc lights, pendulums, dioramas, photographs, iodine, gunpowder, seaweed ash, and cotton from India. By 1790, the stuff is leaving here for Britain by the ton. At first, it's finished articles like shirts going back to England for the rich to wear. But as all that Industrial Revolution textile machinery gets into high gear, back in the UK, we're into mass marketing. And that's a very different story. See, this may all look very picturesque, but you just know it isn't going to keep up with production lines and steam-driven machinery and order books. I mean, the Indian growers can't guarantee a crop, the packaging falls apart, and with roads the way they are out here, regular delivery is in your dreams. None of which helps British cloth manufacturers, tearing their hair out because they've got a market growing like topsy. It's enough to turn an English mill owner to drink. Fortunately, bootleg gin saves the day. No, not this kind. The kind invented around 1793 by a penniless American called Eli Whitney. A cotton gin, a machine that takes the seeds out of cotton automatically. A bit like that. Whitney's gin de-seeds cotton 300 times faster than a human can, so the price of American cotton goes through the floor. And then when everybody bootlegs Whitney's gin, so does the price of a gin. And that's the end of India. That switch to cheap American cotton really boosted the economy of the southern states and expanded cotton growing until there was almost nothing else going on there. None of which helps Whitney very much, who early on has switched from gins to muskets anyway, and a new French idea for making guns with interchangeable parts, so that if a bit breaks in battle, you just slam in a replacement. Well, this idea finally makes Whitney a lot of money. And given the fact that everybody has pirated his gin idea, and getting in debt and practically starving, he must have thought it was about time. Okay, so you saw it coming. Yes, time clocks. And back then, clockmaking is a very time-consuming business. Till Eli Whitney's interchangeable parts idea gets around. And suddenly, now everybody can know what time it is. Because with a few lathes and patterns and measuring gauges, you can churn out cheap wooden clocks made of interchangeable parts till it's time for the cows to come home. In 1816, a young fellow named Chauncey Jerome sets up shop in New England and uses the same technique. But this time, instead of wood, he uses sheets of brass and gets machines to cut out the patterns for each bit by the thousand. Jerome's production line approach turns the household clock into the world's first consumer durable. And since these brass clocks only cost him 50 cents to make, and they can sell for 5 times that, financially speaking, Jerome is going to be in like Flynn. This is a Jerome clock. Nice, isn't it? You may even have one in your family. Wouldn't be surprising, given the fact that in 1 year, Chauncey's factory turns out 200,000 of them. And by the end of his life, he's sold millions all over the world, from London to Sydney. So he ends up rich, right? Wrong. Chauncey's too successful. So when there's a dip in the market, he has to take out a gigantic loan from a fellow who's recently made rather a lot of money. A little bit later on, when this guy discovers that most of his money is being used to pay off Chauncey's debts, well, he pulls out, declares bankruptcy, and for Jerome, time has run out. And on that note, how's our schedule? Smithson's crystals, Curie's radium, sonar protecting ships welded by acetylene that leads to arc lights and pendulums so stargazers can photograph the sky, with daguerreotypes using iodine from seaweed, which gets burnt for potash used on cotton, which is processed by the gin invented by Whitney, whose interchangeability ideas kick off poor old Chauncey Jerome. Meanwhile, Jerome's erstwhile backer, the man who pulled out, remember? He's a real sharp type, a man known as the Prince of Humbug, a person for whom the ups and downs of the investment world are just one big three-ring circus. The three-ring circus is, after all, invented by the Prince of Humbug, a.k.a. P.T. Barnum, who starts in showbiz with a freak show. Then he finds a 2-foot-high man he calls Tom Thumb and shows him off to European royalty. But in 1880, his pièce de résistance is the greatest show on earth. Earlier on, in 1850, Barnum makes a good deal of money as the American tour manager for the biggest thing in music maybe till Elvis, an opera singer known as the Swedish Nightingale. Jenny Lind, one of the greatest singers who ever lived. Miss Lind's tour is so successful, people buy tickets just to buy tickets. Of course, the whole thing is brilliantly stage managed by the Prince of Humbug himself, who takes a hefty cut. The phrase musical notes takes on a whole new meaning. And speaking of notes, another musical genius with an interest in cash gets an offer from London to write an opera for Lind, which he jumps at because foreign commissions like that pay 7 times what he gets from La Scala back home in Italy. Giuseppe Verdi's opera, starring Lind to the usual rapturous audiences, is called I Masnadieri. And if you've never heard of it, that's because some people say, without Jenny Lind, it would have bombed. Point is what it says about Verdi. Like, he gets away with a lot. I'm not saying he isn't one of the greatest operatic geniuses of all time, but what he tends to write about, given what's going on at the time, is, to say the very least, dangerous lunacy. Let me tell you about what's going on at the time and why Verdi's a lunatic. In 1847, when he and Lind get together, the Austrians are occupying Italy, right? So here's Verdi writing stuff with choruses called Long Live Italy, and storylines about the Israelites in captivity, and arias about the fight for freedom. One opera, Joan of Arc, is about how to chuck out an occupying power. OK, he's camouflaging it all by setting the things in France or Israel or even America. But you'd have to be tone deaf not to get the message behind Verdi's political pitch. About the only word missing from all this nationalistic libretto stuff is the word get it. You see the point. I mean, it's a wonder Verdi makes it to the podium, let alone stay out of jail long enough to receive a letter in 1869 from the Cairo Opera House asking him if he'll whistle up a new opera for His Excellency, the Khedive of Egypt. Here's the man himself, who probably has 3 reasons for asking Verdi. Number 1, Verdi's famous, and the Khedive is not. Number 2, this guy, the Khedive's boss, Turkish Sultan Abdul Aziz, who has the Khedive well under his thumb, and the Khedive wants out from under. Besides which, the Khedive is keen to make Egypt look less like a third-rate run-down dump, which at the time it is. So the offer to Verdi is, do something Egyptian and nationalist, which, as you know, Verdi's good at. And as regards the fee, well, it's kind of open your wallet and repeat after me, help yourself. So Verdi obliges, with the most successful opera ever written and called Aida. Unfortunately, Verdi delivers Aida too late for the Khedive's 3rd reason for asking him, which is to celebrate the inauguration of another great Egyptian showpiece, the Suez Canal. When it opens in 1869, it's the 9th wonder of the world, It brings East and West 6 weeks closer because now you don't have to go around Africa. And it brings Thomas Cook into the story, because Cook is one of the nobodies who goes to the opening of the canal. Now, the red carpet gets rolled out for princes and ambassadors and assorted entertainment megastars, but rubberneckers like Cook get to pay their own way and to spend a day here on the Mediterranean island of Malta en route. Not long afterwards, Thomas Cook Limited are starting to run the Cook's tours they've done ever since, and they've opened an office here in Malta. And of course, one of the tours they're offering is Egypt, and of course, the canal, which, as ninth wonder of the world, is well worth your package to $1. Let me show you what you get for your money. Here it is, the high-tech amazement of the age, 100 miles long, starting at an unknown village that becomes Port Said, then through the desert, hitting various lakes on the way, one of which gets a new town named after the Khedive, Ismailia. Then through a final ridge, and the Mediterranean is finally joined to the Red Sea. 25,000 labourers, 10 years to build, and runs Egypt into so much debt the Khedive has to sell his shares. A lot of new harbours are built, as well as a lot of new lighthouses. They even build another canal all the way from the Nile to provide drinking water for the workers. But the thing about the Suez Canal is, there may be no question that historically speaking it's the greatest idea since shish kebab. The question is, whose idea? The French engineer who actually builds it is a guy called Ferdinand de Lesseps, who has a great "I thought of it first" row with another engineer. And his hero is yet another Suez Canal wannabe, who by the strangest coincidence has a couple of brothers here in Malta. And this third person also claims to have designed the canal. Name of Henry Saint-Simon, a curious character to say the least. At one point, Saint-Simon shoots himself in the head 6 times and survives. Then he invents a new version of the Catholic religion strictly for businessmen, and finally he comes up with a totally new scientific view of history. Now, Saint-Simon's secretary, a fellow called Auguste Comte, another loony, and the last, I promise, regards Saint-Simon as a kind of world-class genius, the guru of all time. Speaking of which, India. Now, Auguste Comte never actually visited India. He married a hooker and lived unhappily ever after. But India illustrates Comte's ideas rather well. Well, that's my excuse. And now for his world-changing contribution to science. Comte follows up on Saint-Simon's scientific view of history. Look around you, he says, at museums and such, which we don't have to because what Comte is talking about is all around you here in India, and you see that humanity's gone through 3 historical stages. To start with, we all go through the theological stage, with this kind of stuff. Gods and spirits and other such supernatural mumbo-jumbo, says Comte. That's the first of the 3 stages of development. The second is what he calls the metaphysical stage, the half-theological stage, when people discover how to harness the basic forces of nature, like steam power, for instance, or gravity, electricity, or magnetism, with some form of God kind of pulling the levers behind the scenes. And finally, says Comte, we get to the scientific stage. No mumbo-jumbo, no hobgoblins, no deities writing the laws of nature, just rational, scientific observation of how all the bits of the world fit together. The thing is, back at the theological stage of development, there's no way people can be scientific. There are no instruments that you would call instruments. And since nobody believes in stuff like natural laws that can be investigated, there aren't. And they don't. At the metaphysical stage of steam power and such, they just don't have the science to find out what the mystery forces of nature actually are, so they leave that side of things to God. On humanity's great journey from the past, says Comte, All you can ever say is people at different times see things differently. And he clinches that argument like this. The ultimate science has to be a science that looks at the individual view that each individual has, and at how all the individual views add up to how a society works at any one time. So the ultimate science has to be the science of human behavior, which Kant invents and calls sociology. And he says when you're looking at how a person functions, all you can go on is their view of the world, and that depends on their point of view. There are no absolutes. On the subject of absolutes, Buddhism's all about that. You know, no absolutes. No centre to the universe. Nothing but, nothingness? Buddhism is attractive to the guy who takes over from Kant, because Buddhism represents a point of view that kind of says there's no point of view. The fellow who turns that into a science is the professor of physics at the University of Vienna in 1895. Ernst Mach, famous for his popular science lectures. One of which is not a million miles from what these shows are all about, the accidental nature of discovery. Anyway, Mach takes Kant's ideas to their logical conclusion. First of all, Mach looked at how you view the world from a sensory point of view, by whirling people around blindfold and seeing what that does to them. Then Mach decides to take on bigger things, like how you view the entire universe. Take Newton's apple, for instance. Say you drop the apple. Okay, no problem. Here it is, falling. Except, due to the fact that the Earth spins as it travels in space, the apple's really going this way. Unless, that is, the solar system happens to be turning like this as it travels through space, so that the apple's doing this. Mind you, if our galaxy's turning, then the apple's really turning. Unless our local section of the cosmos is going this way, in which case that's what the apple's doing. Unless the universe is expanding and contracting. So, unless you know your frame of reference, you can't say the apple's falling, or say anything. You see the Buddhist connection. Without a frame of reference, all you get is the local effect, which is no use to anybody. Certainly not the hard heads in science. So Mach comes up with a view of how to view that somebody else calls Mach's principle, and that says everything in the cosmos is affected by everything else, which means that anything you ever experience is going to be strictly relative. You've already guessed, I'm sure, who the somebody else is. The most famous scientist ever, who writes Mach's obituary and who says all physicists get Mach in their mother's milk, and who turns all this philosophy and science and history and stuff I've been on about into an idea that you could say puts the totality of only everything, everywhere, into an entirely new light. Albert Einstein's the name. Relativity is the game. See, Einstein reckons that if everything in the cosmos is affected by everything else, then that should include everything, including light, which Einstein reckons is affected by gravity. Now, there's only one way to check that. So on May the 29th, 1919, they do. With this. An eclipse. Here's the partial eclipse track, and here's the total eclipse track. So here, on Prince's Island, they photograph the moment of total eclipse, when, because of the darkness, the stars are visible in the sky. Now, earlier on, they've taken a shot of the same stars when the sun wasn't in the sky. Look, here's a couple, see? Printed black on white to make them easier to make out. Now, here comes the incredibly minute bit of detail that so often changes the course of history. They come back from Prince's Island with this photograph. Remember, it's all black on white. There's the eclipsed sun, and there's those two same stars. Now, because everything's so incredibly small, you blow those pictures up 300 times, and you get this. Here's one of the stars when the sun wasn't in that bit of the sky. And here's the same star when the sun was there. See that tiny shift? That's because in the eclipse photos, the light from the star is coming past the sun and being bent by the sun's gravity. So the star position seems to change. Thanks to that minute displacement, everything in existence has changed. Well, that's it. Thanks to the Smithsonian and sonar, welding, ash from seaweed, interchangeable parts for clocks, the world of opera, gurus, and Einstein's theory of the gravity effect, we've come from the light of knowledge to the knowledge of light. Because of which, it's Einstein's universe now, not Newton's anymore. So you can drop the apple.